So thank you for the opportunity for this invited speech in VSIP. The title of this speech is Recent Trends in Artifact Detection Removal for Biomedical Signal Processing and Analysis. I'm an associate professor in the Department of Electrical and Electronic Engineering at Independent University, Bangladesh. And I'm also heading one small research group known as Biomedical Instrumentation Signal Processing Lab at the same university. So moving on, the outline of my presentation. So I will briefly talk about the background, motivation, and challenges of biomedical signal processing. And then we'll talk about the classification of different types of biosignals. Then we'll talk about different existing state-of-the-art methods for the removal of artifacts from biomedical signals and the impact of artifact removal on the decision-making part, and what are the available artifact removal toolboxes available online. Then I will conclude with the challenges and the recommendation. So the origin of common biological signal, it is based on different types of organ in a human body. So for example, if you are recording from brain, then it can be an electric signal or a magnetic signal. So we can have an electrical activity of the brain, which is known as EEG, which means electroencephalogram. So the name of this kind of signal is based on this format. So the type of the signal, whether it is electrical activity or mechanical activity or sound activity. So you start with this prefix, and the name of the organ in Latin. If it is an heart, then we use cardio. If it is a brain, then we use encephalo. If it is muscle, then we use myo, and so on and so forth. So finally, the type of the presentation through gram, graph, or graphy. So for example, ECG will be meaning that electrical recording of the electrical activity of heart or cardio. EEG will be the electrical activity of encephalo, that is brain, and EMG means electrical activity of muscle or myo. So this is how the naming of the biomedical signals are mentioned. So although there are different types of biomedical signal based on their nature, whether it's electric, magnetic, or chemical, mechanical, acoustic, but in this particular talks, I will mostly focus on the electrical activities of different organs. So what is the motivation of this? So obviously, we have the signals, biomedical signals are often recorded from the patients, and then we process the signal and then make some decision. So in a nutshell, the processing means actually a detection of artifact and removal of artifact from the signal, which is acting as a noise. Why it is required? Because in different application, we basically record biomedical signals, and in order to make a accurate decision, we have to get rid of all the unnecessary components such as artifact and noises. So start from a patient monitoring in ICU or disease diagnosis, or in preventive healthcare, or in brain-computer interface application, or in treatment and rehabilitation, or basic understanding of any particular organ's physiology and function. We often do need to have signal processing for the biomedical signals. So what are the challenges of biomedical signals? You can see this figure, which actually says that the noise amplitude is quite higher than the biomedical signals such as ECG, EEG, or EMG, which means that biomedical signals are mostly have very low SNR, signal to noise ratio, and they are highly non-stationary and non-linear, which means that the signal properties changes over time. The frequency component of the signal changes over time, and it has diverse type of noise, not only one type of artifact, or there are diverse types of artifact. And the worst scenario is that your noise artifacts, they overlap both in signal, in spectral and temporal domain with your signal of interest. So which means that traditional signal processing technique or the digital filtering, traditional filtering will not work if they are overlapping in a spectral domain. And these artifacts or noises, they will lead false alarms and errors, which will eventually they can mislead the diagnosis of your of any disease, or they will give you wrong information about the treatment or control of any external devices. So example, heart electroencephalogram. So these are some of the common noises recorded in ECG, like the baseline wonder or power line interference noise from the 50 hertz or 60 hertz power supply source, and then muscle noise or the myogram, contaminating the electrocardiogram. And then this is an example of your EMG or electromyogram, where you can see that EMG can be recorded from the surface or from the inside in an invasive way. However, these raw EMG signals are actually a combination of different types of motor unit action potential or so-called muscle signal. This is an example of electrophilogram. That means your eyeball movement of your eye can generate some kind of potential deflection, and they can be used for a diagnosis of eye-related disease, or they can be also used to control some external devices. The most important and most difficult biomedical signal among all of them is actually the brain signal. The reason is that brain signal has the lowest SNR among all the biomedical signal. And you can record brain signal in a different way. In a non-invasive, you can record the electrical activities of the brain, which is known as EEG. If you are recording the magnetic field, that is known as MEG. And in an invasive way, you can have a subscalp EEG. So for example, the electrodes will be on top of your brain. So if it is a semi-invasive technique, or the electrons might be inside your brain, which is known as intracortical implant or ECOG. So you see that different types of brain recording signal have different bandwidth and different amplitude range. Among them, the scalp EEG or EEG, simply called EEG, it has the lowest amplitude, and therefore it is very noisy. The reason that we'll focus more on EEG artifact detection and removal in this particular talk is because EEG is actually most popular among all the brain recording techniques, and among all biomedical signals, EEG has the lowest SNR. So therefore, it is very noisy and very difficult to process and make sense out of the EEG recordings. The reason it is very popular because it is low cost, it is non-invasive. It is easy to use, and it has fine temporal resolution. So EEG is actually a combination of different non-overlapping frequency bands, which are known as delta, theta, alpha, beta, gamma. So the range of EEG signal is mostly from have mostly EEG rhythms, and then there are other types of signal recorded in EEG, which is transient signals, which has a lower duration, and those transients are often some kind of events, can be detected for diagnosis of any disease. So let's see that what are the different types of artifact or noise present in EEG or subscalp or scalp EEG signal. So artifacts are actually defined as mentioned that these are kind of noise. For EEG signal, the artifacts can be defined as an unwanted signal that are generating or originating from some non-neural or non-brain source. Okay. So if an ECG, if it is picked up by the electrodes for EEG, those ECG signal will be denoted as artifact, because ECG is supposed to be from the heart, but for when you are recording EEG, it should be only from the neural or brain source, not from any other source. So you have artifacts based on their appearance. You can have artifacts, appearing all the channel, the same artifact appearing all the channel, which are known as global artifacts. You can have only one instance, a certain artifact. It can be an irregular type of or local artifacts, or you can have an artifact that has very periodic activities or regular. So for example, in EEG, when you are recording EEG, you will find that the cardiac activity or ECG, they are also coming as an artifact, which are regular or periodic activities. So the artifact types and sources can be eventually divided into two different types. One is the physiological or internal source, and another is the extra physiological or external. So external source refers to instrumental, because of the electronics, recording electronics, because of the environment, or because of the movement of the subject. So the challenge with EEG signal processing, as you can see that here, EEG has the lowest amplitude among all EOG, CG, and EMG, among all the other types of biomedical signals. So that is very, very noisy. very low SNR. So what does actually analysis and processing of biomedical signal means? Analysis means obviously measurement of signal, different signal properties, or looking at the signal in other than the time domain, like in frequency or in wavelength domain or in other some kind of domain. And processing eventually meaning that you want to remove the unwanted noise, artifacts, or interference from the field, from the signal, so that you improve your signal quality. Eventually, you will be able to extract specific or important information or detect useful events. So the traditional, signal processing techniques are like digital filtering, typical FIR or IR filter. You can use a power spectral density, Fourier transform based power spectral density to see the characteristics in frequency domain. You can use adaptive filtering, which requires an additional use of reference channel. You can use some advanced filtering type like Wiener, Kalman, or particle filtering, which requires some prior information. You can use a blind source separation technique to actually get rid of the artifact through independent component analysis or canonical component analysis. And then there are some time series analysis techniques as well, such as wavelet transform or short-term Fourier transform based spectrogram, to look at both time and frequency signal, time and frequency information of the signal at the same time. And then there are some empirical techniques, which is based on, for example, Hilbert-Wang transform or empirical mode decomposition. So these are some of the commonly used artifact removal techniques so far that have been used, and some of them, some of the researchers, they have used hybrid methods, combination of 2 or more methods where they exploit the advantage of individual methods. However, you understand that when you are combining 2 or more methods, that the computational complexity of your method it becomes higher. Or sometimes, so it is if you are looking for an online or real-time processing, it is very difficult to manage those if you have a very high computational complexity. So the issues or with the existing removal technique is that most of the literature, they actually talk about only one type of artifact removal. For example, they talk about eye blink removal from EEG signal, or muscle artifact removal from EEG signal. So which means that in order to remove the other types, you need to apply other algorithms, other different algorithms, which may not be feasible in a real scenario because you don't have time so many times. So for each of the artifact, you cannot allocate different types of algorithm. Your algorithm should be robust enough to remove most of the artifacts present, right? Irrespective of the type of the artifact. Sometimes you need a reference channel if you're using adaptive filtering, for example, which sometimes this additional reference channel or recording of reference signal may not be viable. Sometimes these ICA techniques, most of the ICA techniques, independent component analysis techniques, they often require manual intervention, which is not suitable for real-time processing. Sometimes the methods that have been described in the literature, there was not enough quantitative evaluation to assess those methods. And then there are lack of adequate dataset used, which actually question the efficacy of those methods. So example, you can take a look at your power spectral density to understand the effect of any particular filtering. In this case, we have applied a notch filter on ECG signal, which has been contaminated with a 50 Hz power supply noise and its harmonics. So this is in time domain, this is how it looks like. In frequency domain, you see that before applying the application of the filter, there was a 50 Hz and 100 Hz spikes. But after removing those through a notch filter, through PSD, you can understand that these peaks have been gone. They have gone. So this is one way to analyze the signal through PSD. So this is example of a short-time Fourier transform-based spectrogram when you want to see your signal from both time and frequency domain perspective at the same time. So you apply this kind of spectrogram through where we have both time and frequency resolution at the same time. This is an example of adaptive filter where you can, if you have in an EEG signal, often the electrophilogram or ECG artifact, they come, they are very obvious in EEG signal. And if you want to remove them, what you can do, you can separately record those signals as a reference signal channel, and then you have an artifactual EEG. For example, here you have ECG artifact contaminated EEG signal, and you have an additional recording of the ECG signal itself. And then you apply the adaptive filter, where the filter's coefficient can be adaptive, can adapt itself, so that your ECG peaks now have gone after you apply this adaptive filter, right? So where the ECG pulses now have been removed. Then we have an application of independent component analysis, or ICA. It is the most popularly used artifact removal technique from EEG, and what it does, it requires multiple channel recording at the same time. It cannot work on a single channel. So let's say that it is a multiple EEG recording for different channel, and then after applying ICA, it actually decomposes signals into different independent components. The independent components means they are statistically independent from each other, and from that you understand that you can identify a eye blink artifact or muscle artifact, and then you can get rid of them before you apply the inverse ICA to reconstruct back your signal, where in this signal you have got rid of both muscle artifact and blink artifact. Wavelet transform is another advanced signal processing technique that are often used to analyze and to decompose signals in wavelet domain to see if there is any artifact or not, and then apply some kind of thresholding technique on the wavelet coefficient to get rid of artifact and to reconstruct the artifact-free original signal. So the idea is that wavelet transform can be used for a single channel. It does not require multiple channels, which is a good, good thing as far as low channel, when you have low channel signals are available, low number of channels. So this is an example where, as mentioned before, that EEG is actually a combination of different non-overlapping frequency bands known as EEG rhythm. And once you apply this wavelet decomposition or wavelet transform, it actually decomposed into some approximate coefficient, and some of these are detailed coefficients. So detailed coefficients are representing higher frequency component, whereas the approximate coefficient, they are representing low frequency. So you can see that this A6, which is from 0 to 4 Hertz, is same as the delta rhythm. And similarly, different coefficient, level of coefficient actually, representing different EEG signal rhythm. And then you can find out if there is any artifact in these particular frequency bands, then you can apply thresholding technique to get rid of those, and then finally you can reconstruct back to get the original signal, which is an artifact-free or artifact-reduced signal. Another technique known as empirical mode decomposition, which relies on Hilbert-Wang transform. And the good thing about Hilbert-Wang empirical mode decomposition is that it does not require any basis function, unlike wavelet transform. So it is a more like data-driven technique. However, it is still empirical mode. And what it does, it decomposes the original signal into different, IMF, which is known as intrinsic mode function. And through IMF, you can identify if there is any particular artifact. For example, here, these are actually artifact component, right? The eye blink. So you can get rid of, during reconstruction, back to the original domain, you can get rid of IMF4 or IMF5, and then you can reconstruct back your signal, which will be artifact-free. And then people have proposed to combine 2 or more methods to exploit the individual advantage of those methods as a hybrid method to detect or remove artifact. So for example, the first one, this block diagram says that you can use the combination of BSS, blind source separation technique, such as ICA, independent component analysis, or CCA, canonical correlation analysis. You can use this BSS method with the help of wavelet transform, like discrete wavelet transform, which is known as wavelet enhanced BSS method, to remove artifact like this. And similarly, you can use EMD-based BSS method to remove artifact through this process. And then people have said, okay, why not combining the BSS with some machine learning techniques such as SVM, support vector machine, to detect and remove artifact. And then people also proposed, okay, BSS can be combined, accompanied with regression technique to, similar to adaptive filtering technique to get rid of the artifact. So this is an example of how the artifact removal can help in the next stage decision making of your system, right? In biomedical application, right? So where we have taken an example of an epilepsy diagnosis or epilepsy seizure detection, okay? So you see that this is a reference signal where the first half is seizure activities followed by, no seizure or simple EEG. And then this part is without any artifact. So then we have added some artifact on the signal intentionally to see what happens. And then this is the after removal of the artifact through some removal technique. So the idea is that before the signal was contaminated with artifact, the seizure activities and your non-seizure activities, they can easily be identified through some feature like sample entropy, right? If you apply a simple threshold, then you see that below threshold are actually representing the seizure activities, and sample entropy above the threshold value representing normal brain activities. On the other hand, when the signal is corrupted with so many artifacts, you see that some of the during your non-seizure activities, some of the sample entropy, they come below the threshold level. So which means there are more false alarm now. After you remove the artifact as much as possible, your number of false alarm can be reduced. You see that previously, before removal of artifact, there were so many false alarm. Now there is only 2 false alarm. So you can improve the false alarm, for example, as high as 40 to 50% improvement as far as the false alarm is concerned. And your seizure detection also, the ROC curve, super operating characteristics curve, also say that after artifact removal, your detection of epilepsy seizure has increased or has been better. So this is another example where it talks about the impact of the artifact removal on brain-computer interface performance. So BCI often used for rehabilitation, for entertainment, and for different treatment as well. So it says that after artifact removal, your signal to noise and distortion ratio, or SNDR, has improved. Your ROC has improved after artifact removal, which means that your error rate has been reduced after the artifacts are removed. So this is a clear evidence that artifact detection and removal can enhance the later stage signal processing and eventually will help you to diagnose or to help you to make a decision which is much accurate. So these are some of the examples of the available artifact removal toolbox available online free, and most of them are compatible with MATLAB. So some of them we have actually reported here. All these data have been taken from one of my book chapters published in last year in Springer. So if you are interested, then you can take a look at this particular reference, where you can find out all the name of the toolbox and how to find out and what are the different types of biosignal they are addressing, what is the method they are using. And you can see that most of them, they are using ICA. And what are the type of artifact they are addressing. So if you take a look at this particular column, you will find that most of them, so I'll keep going in the next slide as well. So most of them, they are using ICA, or BSS means ICA, blind source separation. ICA is there, ICA is there. So ICA has been the most popularly used method. So I'll just skip this thing, the same toolboxes. So finally, if we come to the conclusion, we understand that the next challenge will be eventually people want to record signals for preventive healthcare or for a long time monitoring. So that means that time the recording will be mostly ambulatory, which means the subject will be allowed to move freely, and then there are some wireless sensors attached to the to their body, to record those biomedical signals, which means that there will be a lot of more artifacts generating due to the motion of the artifact, motion of the subject, which is known as motion artifacts. And therefore, the computational complexity of those removing artifacts each and every time, so it will be very, very difficult. And you have to take care of the computational complexity when you're talking about real-time processing or real-time decision-making or on-the-chip, on-the-fly decision-making. So you have to consider the computational complexity of your artifact removal method. You have to also consider the data storage as well for future use for a predictive healthcare system. The cost is obviously one issue, whether your system is user-friendly or not. So you have to always, make a decision between and trade off between the performance of your system and the complexity, cost, and feasibility. And you also should look at the robustness of your signal processing algorithm that you are proposing. So my recommendation would be you should build an application-specific model, and you should also should talk about what are the specific artifacts that will eventually hamper those signals. So you only are going to remove only those artifacts that are eventually going to hamper your signal. Otherwise, you don't need to remove all the types of artifacts every time if they are not hampering your signals or decision making. So you should also have some standard performance evaluation so that others can compare with theirs method. You should always have the ground truth data, otherwise you would not evaluate your methods performance in a fair way. People these days, obviously, they are considering machine learning and AI, or some of them, they are also considering deep learning or deep convolution neural network to get rid of this artifact and eventually make the decisions. So I think the future is the use of the CNN, but at the same time, you should understand that how the signals are, what is the physical interpretation of those models and whether they are robust or not. So some of the selected references, and I think that's it from my side. Thank you so much.